Let's now consider layer 2 of the OSI model, the data link layer. And it's important to understand that the data link layer has two sub-layers. Specifically, we have the LLC, the logical link control sublayer, as well as the MAC, the MAC, or the media access control sublayer. And each of these sublayers have their own responsibilities. First, let's consider the MAC sublayer. One thing that the MAC sublayer is concerned with is physical addressing, specifically a MAC address. Inside of a networked device where you have a network interface card, burned in by the factory into that network interface card is a unique address. It's called a media access control address. The idea is that no two network interface cards in the world have identical MAC addresses. It's a way to make each device completely unique. And it's a 48-bit address, but we represent those bits typically as hexadecimal digits. That way we have 12 hexadecimal digits representing this 48-bit MAC address that's burned in to the network interface card. Something else that we're concerned with at the MAC sublayer is the logical topology. At the physical layer, we're concerned with the physical topology, like a bus, a star, a ring. Well, physical topologies are how things physically interconnect, but logically they might operate differently. For example, an Ethernet hub has all of its ports on the same segment, just like a physical bus would. We're using carrier sense multiple access with collision detection on an Ethernet hub. Physically, it's a star. Everybody's plugging into a hub, but logically, it's still working like a bus. Another example would be a MAU, a media access unit used in older token ring networks. Physically, we connect it as a star. Everybody connects into the MAU, but within the MAU, within the media access unit, a token is circulating around. Logically, this is a ring topology. Physically, it's a star topology. The MAC address sublayer is also concerned with the method of transmitting on the medium. For example, with token ring, there is a token that circulates in a ring, a logical ring, from one station to the other. There's a place for data in this token, and if I am in possession of the token right now, and I have data to transmit, I can put my data in that slot in the token, and I pass it around to the next station. And if it's destined for that station will remove the data. Now it's empty, and it will send it on to the next station. If it's not for the next station, it just continues to circulate around the ring until it reaches its intended party. With Ethernet, we mentioned carrier sense multiple access with collision detection. That's the way that traditional Ethernet worked when we had a bus topology, or even a hub would work this way. What we have are multiple devices that are sharing the same Ethernet segment. And there can be only one Ethernet frame on a segment at any one time. And to make sure that it's okay to transmit at the moment, a device will listen for a brief period of time to see if the coast is clear. If nobody else is transmitting, then a PC might conclude it's okay for me to transmit, and off it goes. But what if two PCs on the network on the same shared segment, what if they are listening to the same period of silence? They could simultaneously conclude that it's clear to transmit, and they both transmit at about the same time. What happens? A collision happens. Those frames bump into each other, they corrupt one another, and they have to be retransmitted. So CSMA-CD carrier sense, we're listening to the media, we're sensing if there's traffic on the media. Multiple access means that everybody has simultaneous access to the media. We don't have to take turns as we do in token ring. And CD, collision detection, means that if a collision does occur, we can detect that and we can retransmit. Which brings up the question, what's to prevent the retransmission from colliding? Well, let's say PCs A and B transmitted at about the same time, their frames collided. Well, the next time when they retransmit, they're going to set a random back-off timer, and because of the randomness of this timer, they should be transmitting or retransmitting at different times. So statistically, they're probably not going to retransmit at the same time. They're probably not going to collide again. Let's see what's happening at the logical link control sublayer, the LLC sublayer. One thing is connection services. Connection services deals with things like flow control. If a sender is sending data too quickly for the receiver to receive and to process, the receiver could politely ask the sender to please slow down. That's what flow control does for us. Connection services is also concerned with error control. With error control, we can let the sender know that the data I expected to receive was not received, and you might want to retransmit it. Synchronization of transmissions is something else that occurs at the LLC sublayer. In other words, senders and receivers, they need to coordinate when a data frame is transmitted. So I know that I'm looking at the beginning and the end and everything in the middle of this data frame. There are three basic approaches: isochronous, asynchronous, and synchronous. Let's talk about each one of those. First of all, isochronous. Here, the devices, they can look to a common device for clocking. This is an external device, and this external clocking device is going to create fixed time slots. The devices, they can then determine if a time slot has any free space, and if it does, a device can transmit data in that time slot. A big advantage of this isochronous approach is that it has very little overhead. Let's contrast that with asynchronous. With asynchronous synchronization, devices reference their own internal clock instead of looking to an external clock. And the sender is going to send a start and a stop bit that's used to indicate the beginning and the ending of a frame. And we can do some error checking here. Parity bits can be used to check for errors. We could use either odd parity or even parity. Here, let's say that we have 8 data bits, and at the end of those 8 data bits, we have a parity bit. Let's give some values to these bits, and I'll just make it up as we go along. Let's say we have a 1 0 0 1 1 1 0 0. If we're using even parity, then if we add up all of the ones in the data bits and we add to that the parity bit value, if it's a 1, that would add 1 to that total. If that grand total is an even number, then we have some sense of assurance that there's no error because there is an even number of ones if we look at the data bits and the parity bit together. Let's count them up. We have 1, 2, 3, 4 ones in the data bits, and that's an even number. I want this to be even, so I would add a parity bit of 0 to make sure the grand total number of ones happen to be even. If we were using odd parity, then I would need to make this parity bit a 1 so that the grand total number of ones would be an odd number. There is a downside to this approach. Sometimes we might get a false sense of assurance thinking that everything's good, we've done the error checking, there are no errors. However, what if we had a couple of errors? What if this 1 should really have been a 0? And what if this 0 really should have been a 1? In this case, 2 wrongs do not make a right. With these errors that have occurred, and if we're using odd parity, if we add everything up, it's odd. It's still 5. We haven't changed the grand total because we had 2 different errors that gave us that false sense of assurance that everything was good. So realize that while parity bits can give us some assurance that no error has occurred in a frame, it's not a guarantee. A third approach to synchronizing transmissions is synchronous synchronization. With synchronous synchronization, the sender and the receiver, they can share clocking over a separate communications channel. And for error checking, instead of using a parity bit as asynchronous might use, synchronous synchronization can use an algorithm called a CRC, a cyclical redundancy check. And when we think about the data link layer, layer 2, and we're trying to think what sort of physical device lives at the data link layer, the most common device that we normally think of is an Ethernet switch. Let's consider now the operation of an Ethernet